Okay, and we're recording. So so here's where we were last time. We were talking about linear approximations. And so remember, the idea of a linear approximation is it's supposed to be a degree 1 polynomial. So, something kind of linear, right? You might want to say, again, not technically so, but that has the same value and the same first derivatives as the function that you're approximating. So it's a what you might call a first order estimate, right? It's something that's mimicking the function up to first order as much as possible. So we went through and talked about how to do this algebraically last time. Here's the familiar old formula from single variable calculus, and then with the same goal in mind, namely of I want to mimic the function in both value and first derivatives. Same goal in mind. Here's the answer for a multivariable, real valued, but multivariable function. And again, I want to remind you that I think it's a really good exercise. Confirm this for yourself. In other words, plug in x equals a, confirm that you get f of a. Compute all of the partials with respect to all the input variables. Then plug in a, confirm that you get, again, what you're supposed to. Okay, and again, if you have any trouble with that, come to office hours, we'll work it out. And then, for a vector-valued, multivariable function, the general case, in other words, we have this formula right here. And again, there's this, I've had to define some things. I had to define what this thing is. Matrix of partial derivatives, you might call it, denoting it as df. Right, had to define that. In fact, back here, for convenience, we found it useful to define this thing, the gradient vector. Both of these, right now, are just algebraic conveniences. They're algebraic shorthands, right? So we, as of the moment, don't actually know geometrically how to make any sense out of this thing. And likewise, out of this matrix of partial derivatives. Okay. All right. And then where we ended is we talked about the fact that the graph of these approximations is, if you think about it, if you have a function that approximates another function, then the graph of the approximation should, in some sense, kind of mimic something. The graph of the function that you're approximating, right? So if two functions are algebraically similar, they should be geometrically similar, you might say, right? And so here's the linear approximation. The graph of that linear approximation in the single variable case is what we call the tangent line, right? And then likewise, here's our linear approximation for a multivariable function. The graph of that linear approximation, no longer a line, now it's a plane. It's a tangent plane to the graph of the original function. Okay, this is where we ended last time. I hope that all looks familiar. Does everybody remember all this stuff? Okay. All right. So we've been talking about linear approximations now for a bit, and we're now going to ask the question, does this actually... did this really work, or did we just make a bunch of stuff up? I want to go back to something that I deliberately kind of undersold previously. Everything that we said about linear approximations was subject to this little conditional prefix here. If it exists, right? If there is a degree 1 polynomial that mimics the function in value and first derivative. If it exists, well, yeah, sure, then this is what it would have to be. But I can't just write down a formula and therefore assume that it actually does what I want it to do, right? What if we know for a fact from single variable calculus there are plenty of functions that are not differentiable. There is no linear approximation, right? So I can't just go around assuming that this is going to work. I have to first say, first of all, how do I know that such a linear approximation exists at all? And if it does, okay, well then, this has to be it because, look, it satisfies the requirements. Okay. So we're going to entertain that question now. How do we know if our linear approximation actually is legitimately truly a linear approximation. And what does that even mean? Here's bad news. Sorry to have to. So, a lot of things about this course that I think are a little tragic, and one of them, of course, is how much time we don't have, right? Yeah, there's so much material. This stuff, differentiability, is pretty abstract, really, and hard to relate to, and ultimately not so computationally. This is not going to resonate as something. Oh, I can build a better widget out of, right? So this is a little bit mathy and abstract and proofy, and I think it's beautiful math. And tragically, we just don't have time to give it a full treatment. So what I'm going to be doing here is I'm going to basically confess that as far as Math 219 is concerned, the next 2 pages of notes, I don't really know how to write good, appropriate test questions for it. So I do think it's important that you be exposed to the following ideas so you know what we mean when we say differentiable. But I'm going to go through it quickly and with, again, justifying that with the, I don't see any test questions coming up on this next 2 pages. Okay, so here we go. You'll notice that I'm kind of linking the questions of differentiability and linear approximations. And you'll recall that from single variable calculus, that the derivative is what you use to make the linear approximation. You could say that the linear approximation, in some sense, is the motivation for the derivative, right? It's the slope of the tangent line. That's how most people write it down in the first place. Okay, so I'm going to ask a question just to kind of get the ball rolling here. Is this function here differentiable? The function is defined to have value 1 sitting above the axes, directly above the x and y axes. The value of the function is 1. And everywhere else, the value of the function is 0. So over here in the 4th quadrant and in the 1st quadrant, etc., everywhere else, the value of the function is 0. But sitting above the axes, the value of the function is 1. Does everybody see the function I'm talking about? It's kind of a weird function. Is that differentiable? Well, I would hope you're thinking, certainly not. My gosh, look at the thing. It's got a horrifying discontinuity right there at the origin, right? Certainly that's not, come on. Surely it shouldn't be. Here's a disturbing thing about it, though. If you take an algebraic point of view, a lot of people, sort of extrapolating from single variable calculus, would say, well, look, if you can compute the derivatives, then it's differentiable, isn't it? Isn't that what differentiable means? You can compute derivatives. Well, here's the thing. You can compute all of the partial derivatives. Wrong color. You can compute all the partial derivatives. At the origin, if you're sitting here at the origin, if you start moving only in the x direction, well, the function is just constant. The partial derivative in the x direction is 0. Likewise, the partial derivative in the y direction is no problem. The function's constant as you go that way. The partial derivative is 0. So this function, the partial derivatives exist. But we better not call it differentiable because, obviously, right? It's a nightmare of ugliness. So we have a nasty question to entertain, which is, what does it mean for a function to be differentiable? The partial derivatives are not the answer. Right? So, well, what else could it mean? Here's a take a lot of people give, and that is, let's define, error in an approximation in the obvious way. And, if we want linear approximations to be good approximations, what about if the error approaches 0, right? That sounds pretty good. Error is bad. If it goes to 0, isn't that good? Tempting. Here's the thing. This is not actually very good. And here's an easy case in point. Let's look at this function right here. F of x equals 5x. Here's a graph of it. Not to scale exactly, but, whatever. So there's a function, and I could ask reasonably, if I want to do a linear approximation of this function, let's ignore the fact that it's obvious what the linear approximation ought to be. But if I were to entertain as a linear approximation at that point, this function, y equals 3x, there's its graph. Is that a good linear approximation? No, of course not. Silly, right? But check it out. The error, keeping in mind the error is the difference. Let's see here. Error is the difference between the function and the approximation. That error does indeed go to 0, right? I mean, the error is 2x, easily computed, and as x approaches a, right, this error, you can just watch it going down to 0, right? These vertical lines here get smaller and smaller and smaller and smaller and smaller. So what we've got here is, I think, another pretty good demonstration that this is a pretty bad choice too. Right? So we better not base our answer on partial derivatives, and we better not base it on just, as long as the error goes to 0. It's just not good enough. Okay. So we look at another take, and this is a variation. This, we're going to talk about this thing called relative error. Relative error says, how far off is your output value, right? How much error do you have, compared to, divided by, how far away is the input? In other words, how far is this input point x away from the approximating point a? Okay, so it's called relative error. Error in comparison to, it's tempting you're reasonable to suspect that the closer you are, the smaller the error should be anyway. Right? So relative error kind of makes sense. And notice, this does a really good job on our previous example. We were looking at this function, which has that graph. We were looking at this as a candidate linear approximation, obviously poor, but nevertheless, error does approach 0. But this relative error thing, if you look at the relative error there. The relative error is a hard thing to draw a picture. It's that divided by this, right? It's the how far off am I divided by how far away am I? And that relative error approaches 2, which is not 0. And I'm going to argue that this is a way of detecting that, this tangent line here, this candidate linear approximation, it's pointing the wrong way. Because it keeps having error. Sure, the errors get smaller as I get closer, but compared to how far I am away, error. Bad. Right? Okay. So, it turns out, and again, there's way too much to say about this, but it turns out that this, what we wrote down up here, relative error, and asking for that relative error to approach 0, what we call vanishing relative error. This is exactly what we need, as it turns out. This is a wonderful definition for differentiability, aka what it means for a function to have a linear approximation. So here's writing it down. Keep in mind there's relative error. Recall that error is actual value minus estimated value. Recall that estimated value, right, there's a bunch of details in here. Estimated value is the linear approximation, our candidate linear approximation, which of course I'm going to have to edit how I wrote that down with just because of parentheses and all. So this great big monstrosity over here, this is the thing that I need to approach 0. And ultimately, though, it's kind of intimidating to look at, but ultimately all that's saying is I want my relative error to approach 0. That's it. So this is the definition of differentiability. And sadly, it is it's a mouthful and it's a page full, right? And it's awkward to deal with. Because computing these limits. These are multivariable limits. We skipped the section on multivariable limits. Again, we just don't have time. So we just can't make this completely precise. Again, I'm not going to make any test questions that are on this. But this is the big idea of what differentiability is. Hard to work with, though it is. And the good news is, by the way, I have a fix coming up very soon. But anyway, this is the big idea. Pausing for questions. Yes?
Why isn't the definition of differentiability the same as in single variable calculus, like using limits left-hand side and right-hand side? There's a lot to say about that. Ultimately, you can use this as the definition of a derivative in single variable, right? And so it really is the same. It's just that in single variable, you can write it differently in a way that's more convenient. And in single variable, that works. In multivariable, there's just more ways for things to be able to go wrong, and it just doesn't work. So think of it this way: that there's a shorthand that works in single variable. That same shorthand just doesn't work in multivariable. Is really the point. But ultimately, to be precise about it, they are the same definition. Yeah. Okay. Great question. Okay, real quick then, another thing that I want to point out, this numerator up here, I can rewrite that numerator like this. Again, nothing really happened, that's just moving parentheses around. And so notice that numerator, aka the error, right? Error, you can view that as correct value minus approximated value, but you can also view it seems, here, as the actual amount the function changed compared to a linear estimate of how much the function changed. And that's a nice, different way to think about it. These terms are going to be useful. We're going to talk about these. So the actual amount that the function actually changes between our base point and our new point, that's called the increment. This is what we're trying to approximate in some sense. And then our linear estimate, our linear sort of correction term in the linear approximation, this is what we call the differential. And notice we're going to write this sometimes as df, because this is our linear estimate of how much f changes. So just terminology and notation, but anyway, heads up. Okay, now, that's the end of the 2 pages. On which I'm not going to make any test questions, but now back into all fair game stuff. Do we actually have to deal with that monstrosity of a definition day in and day out? I certainly hope not. Good news. There's a related idea that saves us that trouble practically always. As far as this course is concerned, I'm going to say always. And that is the idea of continuous differentiability. And this is different. Continuously differentiable means something very different. It's a stronger condition than differentiability. The first instinct is to think, well, if it's a stronger condition, it's harder for a function to satisfy this condition. Wouldn't that make it even harder to confirm that it's true? Doesn't that mean I have more to check, you would think? Right? The amazing thing is continuous differentiability is really easy to write down, and it's really easy to check. A function's continuously differentiable if all of the partial derivatives exist. Wait a minute. Didn't we just say that we don't trust partial derivatives? I mean, look at this function right here, right? The partial derivatives exist, but this is a terrible function, certainly not differentiable. What's this deal with coming back and talking about the partial derivatives again? I'm going to add in one extra little condition. Those partial derivatives have to be continuous. So merely requiring the partial derivatives to exist tells you almost nothing about the function. This could be the worst function in the world if the partial derivatives merely exist. But once you know they're continuous, you have an awesome function to deal with. This is a nice
nice function. Specifically what we're referring to here, if you have a continuously differentiable function, it immediately follows that function is differentiable. And you don't have to deal with that ugliness on the previous page, big multivariable limit, relative error, etc. Don't have to worry about any of that at all. So this is your ticket. This, in practice, this is how we're going to be checking differentiability. So, for example, is this function here, is that differentiable? Well, I'm going to reason as follows. I can compute all the partials. They're polynomials. Polynomials never fail to exist. Right? Partial derivatives all exist. Cool. The other thing is polynomials are always continuous. So that means that what I've got here, this is a continuously differentiable function, and we have a theorem that says that if it's continuously differentiable, then it's differentiable. And no nasty multivariable limits to be dealt with. Isn't that nice? Okay, how are we doing? Is everybody happy with this? Okay, so again, this is the process that we're going to do in this course. Let me just remind you, by the way, that in this class on exams, and I gave you the whole speech, right? But it's not a class about answers; it's a class about ideas, right? And you always have to show your work and explain your reasoning. If there were an exam question that were this, then you do have to give me all the relevant steps, right? So, for example, if you just say the partial derivatives are polynomials and therefore is differentiable, you kind of missed some key ideas there. It's specifically the continuity of the partial derivatives that you need in order to be able to conclude that it's continuously differentiable. And there's, again, a theorem that specifically says continuous differentiability is what allows us to conclude differentiability, right? So think through that there are important steps, and you got to make sure to explain. Again, when a student writes, this and therefore that, in their head I understand that you may have been thinking all of this. Right? But you got to get it onto the page. You got to document it for full credit. Okay. Yeah.
But do you want us to also calculate all the partials by hand?
It depends on the details of the question. In this case, I think it's what I would call really clear that the polynomials are all, the partials are all polynomials. So here, I wouldn't think it's particularly necessary. If the function were sort of that's kind of a weird looking thing. If it's got some trig in it, if it's got tangent in it somewhere, you better probably go ahead and compute that out. Yeah, good question. Okay. All right, another cool fact. And again, I'm not going to prove this. This is just an assertion. But if a function's differentiable, then it's continuous. That's a nice fact to know. Even more useful, though, is what we call the contrapositive. Do y'all remember the contrapositive? If you have A implies B, the contrapositive is the statement, not B implies not A. Right? And again, I think it's pretty, if A implies B, and if B isn't true, well, wait a second, if B isn't true, how can A be true? You can't have A. If A were true, then B would have to be true. So if B were false, there's no way A could be true. You just have a sort of a contradiction there, right? So the contrapositive, what we have down here, if you have a function that's not continuous, it's not differentiable. It's just immediately, right off the bat, not differentiable. And that's what we've got here, this original function here. This function, obviously not continuous, therefore not differentiable. Yeah. Okay. All right. Okay, so let's talk about this linear approximation again. Here it is. There's our linear approximation. This is our general, right, vector-valued, multivariable linear approximation for a differentiable function. Now, notice at this point, now that I've defined differentiability, right, I can note that I have to restrict this formula only to differentiable functions. function's not differentiable. There is none of this makes any sense if the function's not differentiable. Quick observation, don't forget in some sense, the linear approximation's job, its first job, right, is to approximate f. So, it's got to mimic f. It has to, among other things, have to have the same value as f at the point where I'm approximating. So f of a is L of a. And then notice I can move this over to the other side of the equation. And now I've got a kind of an interesting rephrase here of my linear approximation formula. And I'll point out that what we've got here is a relationship between how much I change the input to the function, namely, I'm starting at the point A, and I'm interested in what happens when I move a little ways over to some presumably nearby point X. That's how much my input changed. And I've related it now to, not the actual output change, but this is our linear estimate. This is our best linear estimate of how much the output has changed. It's not the actual increment, the actual f of x minus f of a. Who knows? But this is our linear estimate. And so we have a relationship here between what we call input differentials, output differentials, or as I like to sort of casually think about it, we've got a relationship between input changes and output changes. And I'll remind you that on our very first day talking about derivatives, this was this was the motivating target. This is what we wanted a derivative to be, some relationship between input changes and output changes. So this matrix of partial derivatives that I've been referring to sort of deliberately, awkwardly, is the derivative. That's what a derivative is. So I think this is a big reveal. df. It's the derivative, aka the derivative matrix, aka the derivative transformation, because it's a linear transformation, of course. Also sometimes referred to as the Jacobian. Somebody mentioned that earlier. And in such cases, usually written as J instead of D. But all the same thing. This is the derivative because it's the thing that turns input changes into output changes. So not really just a notational shorthand, particularly anymore. Now it's a natural thing. This matrix is a natural thing. It's the derivative of the function. Kind of weird, by the way, to think about. I mean, y'all are accustomed to derivatives of single variable functions being functions, other functions, right? Or you might say the value of a derivative has always been a number. Derivatives are the functions that give you, but when you plug in a point, you get numbers. Here, the derivative is not a number. The derivative is a matrix. And it's a little weird. It's a new concept. But ultimately, it really does make a lot of sense. I'll point out that if you, in fact, have a multivariable, right, vector-valued function, and you're talking about input changes and output changes, well, I mean, if you think about it, input changes are unavoidably vectors. Output changes are unavoidably vectors. If a derivative is going to turn one vector into a different vector, I mean, not all that shocking, really, for it to turn out to be a matrix, aka a linear transformation. Everybody buy it? Okay. So here's my picture. Let's see if I can squeeze. I tell you what I can do. Do it like this. Here's my picture. What the derivative is. The derivative is a relationship between input changes, which are vectors in the domain, and output changes, which are vectors in the target. So the derivative matrix, it's not the function that takes a to f of a. That's f, right? That's not what we're talking about. We're talking about the function that takes that vector to this corresponding vector. This is how I visualize, this is how I think about derivative matrices. Everybody okay? Now, one of the awkward things about this way to think about the derivative matrix is that let me say it in words, and you'll see what's awkward about this. Okay, df is the thing that turns how much we change in the input into our linear estimate. Our best that we can do, first order approximation, going to be wrong a little bit, sorry about that, but estimate of how much the output changes, right? So it's a little bit awkward. Obviously, I awkwarded it up for emphasis. But that in mind, I do have a kind of slightly preferred way to think about the derivative matrix, and that is this here. Just take the previous picture, divide by dt. And now, instead of talking about an input discrete change, now we have a rate of change, aka a velocity, right? And we have a rate of change of the output, aka a velocity. And output velocity, input velocity. So the derivative matrix is not a linear approximation here. Here, this is exact. The derivative matrix turns input velocities exactly into output velocities. Rolls off the tongue very nicely, thinking of it that way. And of course, the reason this works is when you were talking about velocities are instantaneous. They're already limits, right? So we don't have to worry about approximations. Yeah. Okay, so this is really my favorite way to think about the derivative matrix. Okay. All right. Real quick, I'll point out you can make the same argument for gradients, right? We had a for the real valued functions, we had a formula for linear approximations. You can move the one term over to the other side, you get this thing. You can say, we have here input differential, and here's our output differential, and so the gradient is the thing that does it. The gradient, therefore, is the derivative. And it's tempting to say, then I guess we have two different formulas. For real valued functions, I guess the gradient's the derivative, and for vector valued functions, I guess the derivative matrix is the derivative. Tempting to say it that way. I'm going to point out that they're really the same thing. At least the derivative matrix is the general version. The gradient is really a special case, because here's what the derivative matrix looks like there. Right, the right-hand side of the equation is derivative matrix times dx, and this being a matrix, this being a vector, this is matrix times vector, and the way you multiply a matrix times a vector, well, the matrix is a single row, and so you're going to kind of go across that row and then down the dx. It's a dot product, right? And if you think about it, the gradient, it's all the same stuff. Just instead of being thought of as a horizontal row matrix that you do matrix multiplication with, it's now thought of as a vertical vector that you do the vector dot product with. It's the exact same arithmetic, though. It's just written and maybe thought of a little bit differently. So anyway, I'm gonna say you can think of the gradient as being a derivative. That's fine. It's sort of an alternative point of view. You're also perfectly welcome to think of the derivative of a real valued function as being, it's just a matrix with a single row, and they're the same. Okay. All right. Okay, moving along. Couple of quick things to say about 2.4. Actually, not very much. In fact, I think I recall this is just a single. There's a few things. Couple of quick things here to start off. and this is a subtlety, this is where linear algebra is going to, the fact that y'all have had an actual course in linear algebra is going to be important. So I'm going to describe a certain weird kind of linearity. And it's tempting to say, well, didn't we just get through agreeing that this is a matrix? Derivative is a matrix, and if it's a matrix, aren't all matrices linear? Wasn't that kind of a big deal the first day of class, right? All matrices are linear. Yes, absolutely. The derivative matrix, clearly linear. I want to talk about something else, though. I want to talk not about the derivative matrix. I want to talk about the act of differentiation. Notice I'm expanding that out here. Right? If you think about what D does something to a function f. We've got to start with a function. Right? D takes a function and it does something to it, the output, the result of which is this thing called df, and df is a matrix. Right, so D, if you think about it, is really a weird thing. DF turns vectors into vectors. D turns functions into matrices. Everybody see that? It's a very, very different thing from the derivative matrix itself. The act of differentiation, very, very different. So the claim I want to make here is that, well, not only are the matrices themselves linear, which is, again, straightforward. But furthermore, D, this function from this weird vector space to this weird vector space, D, also linear. And specifically then, what I mean by linear is this right here. And notice, linear combination of inputs, corresponding linear combination of the outputs. I mean, it's the same notion of linearity. It's just that the inputs are now functions, not vectors. Okay. All right. So I hope this looks relatable. At least I wouldn't expect you would have seen this actual example in linear algebra, but I hope this idea of a function from one vector space to another vector space is a familiar thing. Okay. All right, so let me give you an example. I'm asserting that this differentiation is linear. Here's the example to see it. Well, here's the example to, plausibility check. Here's a couple of functions. F, there's its derivative. Let's see here, I'll use orange. G, there's its derivative. Think that through. Right, there's partial derivatives to be taken. We've got 2 input variables, 2 output variables, which is why we have a 2x2 matrix for the derivative, and various partials of various output coordinates with respect to various input coordinates. You got to think that through. Again, I remind you, got to be ultra careful about accidentally transposing. Don't accidentally transpose it. It wouldn't have made a difference with the first one, but it definitely would have made a difference with the second one. So heads up on that. So make sure you're good with computing those. Now let's look and see, well, what happens if I take a linear combination of those functions? Here's the linear combination. You can just punch that up. And here's its derivative. Again, various partials arranged appropriately. Again, make sure you're good with that. And now, did it work? Did we get the linearity that we were expecting? And, well, good news. If you take a linear combination of the derivatives versus if you take the derivative of the linear combination, yep, same thing. So it totally works. And you can just, you can check the arithmetic, but the linear combination of the derivatives, the derivative of the linear combination, same. Okay. All right, second little quick thing I want to point to. The book does note various product rule, quotient rule, various cases, this is, I think, very appropriate to just read for yourselves. So look in there and notice that there are certain nice rules that you can use, and make sure that you're familiar with those. You can even, maybe check a couple of them. Again, plausibility argument, just to look at some examples, and they work out. Okay. All right, now where it gets more interesting, though, higher order partials. So y'all have seen higher order derivatives in a Calc 1 class, right? If you have a function, take the derivative, you get another function. That function you could also take a derivative of, right? Well, same thing here. If you have a multivariable function, by the way, we're going to momentarily consider real valued only. Real valued only. But if you have a multivariable function, some expression involving various input variables, if you take a partial derivative, the result is still an expression that has, written in terms of those same input variables. So, if you can take a partial of f, then you can take a partial of a partial of f. And these are called higher order partials, second partials, third partials, etc. Starting with an example, there's a function, there's the x partial, there's the y partial, no problem. We've talked about the notations before, right? Easy algebra. Now, let's just point out that you can take partials of these partials. So, for example, here is the x partial of that function. Then here would be the y partial. I kind of ran out of space. I would have done it over here, but I had to squeeze it to the left here. So let's look carefully at the y partial. The y partial of this thing is that. And let's think about how we should write that down. Well, we're taking the y partial after all. What are we taking a y partial of? We're taking a y partial of the partial of f with respect to x. And one notational option that would seem reasonable is to just kind of smash all these letters together, all these characters together, and people will write it like this. And this has always made me a little uncomfortable. It's just notation, though. So don't sweat it. Where it says squared, nothing's being squared. Exactly, right? This is just in recognition that, we're taking a partial of a partial, and there's two of them there, and it's just a little easier to write it like that than like this. Okay. All right, now also, though, let's not lose sight of the fact we could just as well have written the initial partial derivative as fx. Let's see, how would we take a y partial of that? The act of taking a y partial of something, we can denote with a y subscript, and so that gives us this. So fx, y, people will write as fxy. So either of these is fine. In some contexts, one makes more sense. In some contexts, the other makes more sense. Just use whatever seems most convenient and appropriate in your circumstance. Heads up, though. Notice that the y is. Let's see how the y is kind of on the right there, and it's kind of on the left there, and the x is kind of on the left here, but it's kind of on the right there. That's weird. That's annoying. So think it through, right? Whichever one of these notations you're using in any given particular moment, think about where it comes from to motivate whether the x should be on the left or the right, depending on what you're actually computing. Okay. All right, and of course you can do the same for the x partial of the y partial. Again, giving you then sort of two options for how to denote the x partial or the y partial. And again, notice that there's a backwardsness to the notation. Okay, is everybody okay so far? Yeah.
So I noticed the fxy and fyx are the same. Is that always the case?
That's a great question. That's exactly the next thing to notice. In this case, possibly coincidental, one might wonder. Right? These happen to be the same. It turns out this is not a coincidence. It also, though, is not always going to work out like that. It's definitely not a coincidence. What it is that sufficiently nice functions, if you have a function that's sufficiently nice, then rearrange the derivatives however you like. Any sort of rearrangement, and they're going to get the same thing. Take the derivatives in whatever order you like. Okay, now, sadly, I do have to go back and talk about what do we mean by sufficiently nice. Sufficiently nice means however many derivatives you're planning on taking, you need for all of those derivatives, all the way up to that order, you need those partial derivatives to exist and to be continuous. So if you're talking about taking, is the xy and yx, are those the same? Well, then you would need for not only the first partials, but also all of the second partials, all to exist and all to be continuous. That's what we call a C2 function, or in general a CK function. The C is for continuous. Let's do it like this. Yeah, so the C is for continuous, and the K is for how many partials have to be continuous. All right, so there's the result. Everybody happy with that? We're not going to prove this theorem. It's beyond this course, but it's important to know. Okay. Okay. So what do these things look like geometrically? And again, whenever you're creating mathematical constructions, you can write down any definition you want. Knock yourself out. It's a free country, right? But if you want anyone to care, then you have to persuade that there is a way of thinking about this as something that's algebraically, that's geometrically natural or physically natural, something like that. So, what do these second partials look like? Oh gosh. So we're gonna talk about this on graphs, which is hard enough. First some good news, the unmixed second partials, like fxx. It relates to concavity. It's just exactly what you would think it is. You can think it through. I mean, how do you compute fxx? Well, the first thing you do to compute fxx is you say, okay, I'm going to treat y as a constant, and then for the whole rest of the discussion, thinking about fxx, y remains a constant throughout that whole conversation. Because you're taking an x partial, and then after that, you're taking another x partial. Y is just flat constant. So you're literally looking at this curve, the cross-section in the x direction, and you're literally taking single variable derivatives of it. And so this boils down to, hey, what is the second derivative, the regular old single variable second derivative? Well, it's concavity. And here we have, this is clearly concave down, and so that fxx is negative. Just like I say, exactly what you would have thought. And then, of course, if you're going the other direction, if you're looking at fyy, then y is the only variable. X has to be treated as a constant. You're stuck in this plane for that whole conversation, and this cross section is concave up. Fyy therefore is positive. Yeah? Everybody good? Okay. So where it gets weird is if you are interested in what we call a mixed second partial. And mixed means one of the partials with respect to one variable, the other partial with respect to one of the other variables. And I'm going to do just a function of two variables here to keep my pictures, drawable, right? I don't want to get into four-dimensional anything. So, okay, how would I make sense out of this mixed second partial? And there's different ways to think about this. My favorite is to say, well, I have a point of view on how to visualize y partials. Namely, they are slopes of tangent lines. So let me draw some y partials down here. And I'm going to apologize for the fact that this is so hard to draw a good picture. Even with a computer-generated something, there'd be a surface, but it would kind of be getting in our way and confusing really what I want to visualize. So I'm not actually going to draw the graph here. I'm just going to note that wherever we might happen to be looking, at whatever point I'm at, I can talk about what happens as I move in the y direction, right? Y partials are in the Y direction. And I can talk about what that tangent line would look like, and I'm going to draw just the tangent line. We'll piece together what the function's doing after. But there is a tangent line to my not drawn graph. That's the tangent line as I move in the Y direction from that point. And you could do the same to these other points, above there, maybe your tangent line was like that. Above here, maybe your tangent line is like this, et cetera, et cetera. Let's say something like that. Okay, so this is what Y partials look like. So what is an X partial? Well, it's tempting to say, well, I'm going to interpret X partials as being slopes in the X direction. But I would need to then have a graph of the Y partial, which I don't. I just straight up don't have a graph of the Y partial. I have a graph of F. I'm taking the Y partial of F. I can talk about the Y partial from the point of view of the graph of F because I have a graph of F. I do not have a graph of this Y partial whose X partial I'm interested in. So don't even think about trying to make sense out of how the X partial is the slope of the graph of this Y partial. That doesn't make any. We can't visualize that. What we can do though is say we have this alternative interpretation of X partials. X partial says, look, as I start moving in that X direction, how fast are we seeing change in the thing that I'm taking the X partial of? Right? So I can entertain the question of, as I move in the X direction here, see I have drawn in blue, as I move in that X direction, how are these Y slopes changing? Right? And notice what I have drawn here. This slope is very negative, and then still negative but less, and then barely negative, and then 0, and then slightly positive. I appeal to your sense of geometry in this picture that as I move in the X direction, these Y partials are increasing. They're going from negative to less negative to positive, and that's increasing. And if the X partial is measuring, well, if the thing that we're taking the X partial of is increasing, then the X partial is positive. So in this picture here, that mixed second partial is positive. I saw a hand somewhere. Everybody's good? Okay. All right. So this is what a mixed second partial looks like, and the way I like to visualize this is it's like, imagine you have a sheet of paper, but paper doesn't really bend very well. Paper is actually not a very nice substance. But if you had a sheet of rubber, imagine you had a nice stretchy sheet of rubber that bends in all directions, right? And then imagine you're kind of holding it by the corners. What's sort of what this conjures is the idea that I would twist that piece of rubber, right? If I twist it so I'm rotating one side one way and the other side the other way, right? That twist is what we're seeing here. Mixed partials measure a kind of a twisting of the surface. And that is, they have a name for it. It's called torsion. It's a twisting of the graph, again, aka torsion. Okay. Yeah, and I think we're out of time. I'm sorry I went over. I lose track of time. Okay, we're done for today. Drawing the line right there. Y'all have a good one. Have a good weekend. Bet you we have a homework due tonight. Is that right? I think yeah. Okay, good luck getting the homework done. And a reminder, I've got office hours right now. In 10 minutes. Hope to see you there.